chapters, around to 40 book chapters, as much as I can find it. Professor Northoff studies on the relationship between the brain and mind and its various facets. Today, he is going to present a very important speech titled is Common Currency of the Brain and Mind and Spatiotemporal Approach. And I would like to welcome to Professor Georg Northoff to present his speech. Yes, your time.
Yeah, thank you very much also for the nice introduction and the kind words. And actually, I'm just heard it's very warm in your part of the world, and ours it's -5, but at least it's nice. Yeah, my talk, let me just share my screen, and I hope you can all see the screen.
Yeah, it's fine. We do see.
My talk is about more on the systemic level than on the cellular level. But it addresses really a key question of current neuroscience, the relationship between brain and mind. And despite all the research, the huge advances in molecular and cellular neuroscience, and also in systemic neuroscience with the brain imaging, we still really don't know why we have neuronal features transforming into mental states, like consciousness, sense of self, psychotic disorders. So my talk is exactly about that, and I suggest a particular strategy and supported by several lines of data. What we currently do on the systemic level of neuroscience, we really remain, and you can see this here with my little arrow, on the surface of the mind. Yeah, this is really the tip of the iceberg. That's what we also do with brain imaging, fMRI, EEG, MEG, PET, you name it. That's really just the upper 5% of our brain's neuronal activity. However, as we all know, there's also a deeper layer. And that deeper layer remains mostly unconscious, if not non-conscious. And current neuroscience, in particular cognitive neuroscience, often does not take into view this deeper level of brain activity. And the claim is that this deeper level of our brain activity is key for understanding mental features. When I say mental features, I mean a subjective experience of a sense of self, consciousness. You're aware when you listen to my talk, it's afternoon, you you have a certain feeling of pleasure hearing this German accent from somebody in Canada, and so forth. And it is this subjective experience of pleasure or amusement about my accent, which I mean by consciousness or mental features. So my talk will guide you through this approach. And the idea is really that space and time, how the brain constructs its inner space and time, are key for mental features. I will shed more detailed view here in my first part, theoretical background. Then I will give you 3 examples. First, the example is the self, our sense of self. Then the example of consciousness, how we conceive it in temporal spatial terms. And third, the example of psychotic disorders. So let me start with the theoretical background, which is very important for you to understand the kind of model. The kind of model of the brain, which strongly impacts how we design our experiments and analyze our data. So, question is, of course, as you already know, how to link brain and mind. The current strategy, and this is mainly systemic neuroscience I'm talking about, is brain imaging, fMRI, EEG. However, I think it also applies to the cellular level without really being able to make strong claims in that respect. So one of the problems on a more conceptual level, which we're really facing, is that the relationship between neuronal activity and mental activity remains contingent. We have why does neuronal activity is related to mental activity. We currently do not know. One of the ideas is that our mind, our mental life, our inner consciousness is very dynamic. It's continuously changing. William James, stream of consciousness. Then phenomenologists often said that our consciousness has a certain structure, an organization, like figure, background. You perceive me against the background of my office. Yeah, you see the clock, you see the painting, and then you see in front of me. But your consciousness can make a clear difference between the background, the wall, and me as a foreground. So your consciousness must have a certain structure. And that structure has a certain spatial dimension, a topography. Yeah, certain things are emphasized, others are not. However, we approach the brain not in terms of topography, but rather in terms of single regions or single network. Topography would require a whole brain approach, a more holistic approach, and then how you come from the whole brain to the parts. Then often we perceive our brain in static terms, like the average across different time points. That's not dynamic. That we sum up the single trials, add them to each other at different points. That leaves out or cancels out the relative changes between time points. And then we mainly focus on specific contents. You just see what are the neuronal activity when I perceive Georg Northoff talking, but you do not consider the background, the spatial organization, the structure with which I'm talking. So that leaves sort of a gap between the mental and the neuronal level. So how can we cross that gap? So one way is, for instance, to see searching for what is similar and shared by neuronal and mental features. So that is very different from many other approaches these days, which rather look for specific neuronal mental features, underlying mental features, as distinguished from all other neuronal features that are not related to mental states. I choose the opposite way. I look for what is similar, what is shared. This beautiful quote by Nikola Tesla, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. And this is really, so we go back to the basics of nature, of physics, of the universe, of the world. And I say that also applies to the brain. So this is something we formulated last year with many empirical examples. In this paper is temporal spatial dynamics, the common currency of brain and mind. And that's basically the program of this talk. So what do I mean by time and space? Traditionally in neuroscience these days, time and space is just conceived in terms of what are the neural correlates of our perception and cognition of outer time and space. So your brain is very active now when it listens to me and perceives me, but in outer time and space. However, your brain has its own inner time and space. So the brain continuously constructs its own inner time and space. It's like music. Music has its own music piece. Classical composers are a master in constructing the music's inner time. And then how you can synchronize with that time, that's the outer time. So then the focus is really on how does the brain inner time matches with the outer time. Typical example. When I speak very fast, you will not be able to synchronize with me because maybe your brain doesn't have that speed. Or when the music is too fast, you cannot tap the rhythm of the music with your feet. So that means there's a mismatch between your brain's inner time and the music time. However, if they match perfectly, you go with the rhythm, you tap exactly to the beat of the music, inner time of your brain and outer time of the music, perfectly aligned. And you have a feeling, you have a groove, you have a sense of connectedness. Very important. So the alignment is related to a certain feeling, experience, and I will come back to that. So, what is the exactly brain's inner time and space? I don't need to tell you. This, for instance, constructs the spatial topography, the whole brain organization across its different regions and networks. I will give more examples later. Temporal dynamic, you all know this. The way the neuronal activity continuously fluctuates in different frequencies. Faster ones, which we can capture with EEG, slower ones, which we can capture with fMRI in the frequency range of 0.01 Hertz to 0.1 Hertz. Yeah, so we have a whole fluctuations in different frequency ranges of the brain. It's like the sea and its wave of, you know this, of course, Turkey has beautiful seasides. So you have big waves, they're very powerful. You have smaller waves, they're not as powerful. So I will give more examples, specific empirical examples with measurement of these kind of dynamic and topography later in my talk. So that's basically the summary slide. What I say that maybe topography, dynamic, space-time provide the shared features between the neuronal level of the brain and the mental level of the mind. So that's basically what we called common currency in this paper last year. And that's what I now give you some more examples, how such a neuroscience, we call it spatiotemporal neuroscience, could look like. So that's sort of the larger model, and you may be puzzled a little bit, what does Northoff mean by space and time on mental features and so on and so on. I give you now concrete examples, and I will start with the example of self. What is the self? I'm sure this morning you got up, you looked into the mirror, and you weren't even aware, but you had a sense of, oh, it's me. Yeah. And you probably not even aware of that. It's just unconscious. You know it. You take it for granted. However, as a psychiatrist, I'm dealing with people who sometimes experience, oh, this is not me. So they look into the mirror and say, no, this is not me. Yeah, this is somebody else. This could be, as a psychiatrist, I have seen many famous people. Jesus, Buddha, Nefertiti, Mao. Recently in Russia, I encountered Stalin, because I usually, when I travel, I try to also see patients over there with psychiatrists, because it gives me a lot of background. And how is that possible? And these people really experience themselves as these famous, often famous persons. And interestingly, there's also certain cultural variants. So you would not see a Jesus in China, but you see a Buddha in China. Yeah. And vice versa. So the question is, how is that possible? So that really tells you that your sense of self is somehow constructed by your brain, and that construction can go awfully wrong. So what's going on? There's a lot of research on brain imaging of self, on the regions which I recruited doing self-specific stimuli, for instance, your own name, your own face, or trait adjectives, like for me, a scene of Ottawa, snowstorm, -40 is very self-specific. However, for you as Turkish, when you see that picture, it has nothing to do with me. Yeah. And that's basically what you can test. You can probe that in brain imaging. And we did, last year, we did a major meta-analysis of different kinds of studies. You have self-specific stimuli on the body level, for instance, from your interoceptive organs, from when you monitor your own heart rate or your breathing rate, or you have input from your outer body, proprioceptive, your inner outer body boundaries, and of course, mental, you can think about yourself. And this is a very large scale meta-analysis, because we want to figure out which regions are related to what kind of self. So the self sort of on the inner body level, the interoceptive self, recruited, these were, I think, in each of these studies were at least 200-300 imaging fMRI studies. On the interoceptive level, you could see that regions, probably no surprise, bilateral insula, thalamus, dorsal anterior cingulate, parahippocampal gyrus, were strongly recruited. So these are regions sort of which become active when you become aware of your own inner body, like your heartbeat awareness, respiration, breathing awareness. Then we had a second set of independent studies, which were basically more with the outer body boundaries. So this is for people who are in the field, studies by Olaf Blanke and others, where you basically try to your outer border boundaries, that you have out of body experience and things like that. So these studies, which were completely independent of this one, yielded the anterior medial prefrontal cortex, bilateral temporal parietal junction, premotor cortex, and interestingly, as well as the bilateral insula. Then we had a third set of studies, which were the typical self-studies with trade adjectives, as I said, Ottawa snowstorm versus Turkey sun. Yeah, and you had to basically refer them to yourself. And that recruited a lot of the cortical midline structures, part of the default mode network. And interestingly, all those regions which were active here, particularly the right and left insula, as well as the regions from here. So this is a very interesting finding, because what it shows that the regions from a lower level, like interoceptive, are also recruited during the subsequent higher level, like exteroceptive, processing outer body boundaries, proprioceptive. And then you go even further, that on the purely mental level, just in your cognition, you have the same regions again. You see the insular, temporal parietal junction, anterior medial prefrontal cortex, premotor cortex, plus additional region, perigeneal anterior cingulate cortex, posterior cingulate cortex. So this is really amounts to what can be called a nested organization. The regions of the lower level resurface within the next higher level, plus additional region, and so forth. That is reminiscent of the famous Russian dolls. That's what you can see here. So the smaller one is nested within the next larger one, and so forth. And here you see the same on the Chinese side. This is a Chinese crystal ball. You see the fine manufacture is unbelievable craftsmanship here. You see all these are little Chinese balls of different sizes, all nested within each other. So that is very interesting, meaning you seem to have a nested hierarchy of the layer of the self in, by the brain, by these different regions. So meaning there is a spatial organization, a topography to it. It is not just that one single regions or one single network. No, the different overlap, the different regions or networks overlap and are nested within each other. And that goes to different layers of self. I don't need to tell you that this is very reminiscent of, for instance, the kind of layer organization, hierarchical layer organization suggested by Hughlin Jackson at the end of the 19th century. Yeah, and also it has some references to the topography of the ego by Freud. So you see, these are all hierarchical models. The really new things about this is, first, is empirically data-driven, and second, it is really a nested organization. Yeah, it is one layer nested, contained within the respective other. And you will see a similar nested organization you see on the temple side. So I already showed you, when you analyze brain data, you have sort of these different, these are raw data. And often, this is often pre-processed out of the data as pure noise. However, I'm exactly interested in this background noise, because it's not technological artifact, it's neuronal background noise. And I already showed you this one, fluctuations in different frequencies, gamma in EEG, infra-slow in fMRI, 0.01 hertz, 40 and larger hertz in gamma. And what is important, that in these fluctuations, there is a certain pattern. So you analyze the whole time series. You do not analyze just one time point and then average across all other time points like in typical task state, but you average the whole continuum of the time series. Yeah. And then you see a certain structure. Typical. For instance, when you analyze the power spectrum, you see that slower frequencies have stronger power than faster frequencies, which have less power. Typical. You just need to go to the seaside here, the Mediterranean Sea, and you will see big slow waves are extremely powerful. Faster waves you're not afraid of because they're fast and quick and less powerful. And then another thing, so this is what you can analyze with what is called the power law exponent. And you will see in the next slides data on that. And then you also can do what is called the autocorrelation window. Basically, you have the whole time series of your neuronal activity across all time points. And then you can correlate all time points with each other. T1 with T2, T1 with T3, and so forth. And then you will see that, of course, there's a decrease in correlation, but it describes certain time windows. I will come back to that. So why is that relevant? Because what we did, then just in the resting state, we put people in the resting state in fMRI, at a 10 minutes resting state in fMRI, and then we also applied a self-consciousness scale. This is a psychological scale to probe for your degree of awareness about your own self, about your private thoughts, about your social thoughts, and your public scores. And what we found that particularly these cortical midline regions, you can see here the medial prefrontal cortex, posterior cingulate, so the core midline structures of the default mode network correlate with the degree of self-consciousness, meaning the stronger the power in the slow waves, the higher the power law exponent and the higher the degree of self-consciousness. Meaning the slow, powerful waves in your brain are extremely important for maintaining your self-consciousness. That makes sense because your self-consciousness is about continuity, temporal continuity. You remain the same across changes in your environment. Yeah, I'm still the same like 20 years ago. I cannot avoid it because there is a certain temporal continuity and your brain constructs this temporal continuity. Also, I want to focus your attention on each of these lines. So this is frequency, this is power. You see more power in the slower frequencies, and you see huge inter-individual variabilities as each line is one subject. But that's not noise. That is real because we are all inter-individually different. So then again, you see sort of the Russian dolls example. So here you see my other analogy. The self is like a surfer. The surfer likes big, powerful waves because they're temporally continuous and she or he can surf on them and has to align to them. And that's exactly what your self does. So now you say, yeah, but how is that really related to psychological features of self? See, this is where psychiatry becomes very handy because it gives you a lot of interesting phenomena where sort of the self is destabilized. Let me give you the example of anxiety disorders. So this is, of course, you all know this, Edward Munch, the cry. And here we did a meta-analysis of all studies on social anxiety disorder. So social anxiety disorder is a disorder where when you see other people, you become very anxious. You already anticipate, oh, there could be another person, you're anxious and you withdraw. And when you're actually in social context or typical, for instance, I've seen that in many academics when they have to give a talk, particularly in public. So maybe Zoom makes it easier for them. Yeah. So in what we observed, remember the cortical midline structures, medial prefrontal cortex, posterior cingulate, were related with the mental self. And interestingly, in social anxiety disorders, these regions show decreased connectivity. They are less synchronized with each other. So that means that your mental self may become unstable. The slow waves are very unstable and probably shifted to faster waves. So you do not have such a temporal continuity. Yeah, your temporal continuity is sort of disrupted in anxiety, of course, and then you become anxious because you cannot anticipate, you cannot predict, and that's exactly what you see in these patients. So then, interestingly, this is again the meta-analysis just published with a PhD student of mine in Italy, in Florence, Lorenzo. So you see then also during task activity, during multiple task states, you see an increase in activity. So these people have a decreased default mode cortical midline activity in resting state, and then they are hypersensitive to external stimuli, particularly social, emotional stimuli. And that makes sense. So they react too strong and then they get anxious. So that's basically the idea here, that maybe if the mental layer of self is abnormally weak, you show strong anxiety, and then maybe the lower levels, the exoceptive in particular, the interoceptive layer, become relatively strong. So what do you perceive? You perceive strong bodily and interoceptive changes. That's exactly what you see in these patients. Typical example is panic disorder. People come to the emergency room and say, I have a heart attack, but there is no objective sign. Then finally the cardiologist calls the psychiatrist, and the psychiatrist says, oh, seen it many times before, panic disorder. Yeah. So you see how the shift from the mental to the interoceptive layer, because maybe the mental layer is unstable due to the decreased synchronization functional connectivity of the cortical midline structures in these patients. So I hope that gives you an idea how this topography of self might indeed provide a new view on the self, as well as on psychiatric disorders, where you have shifts between the different layers. Ideally, that you would like to use this for differential diagnostic of different self-disturbances in different psychiatric disorders. So this is something we're working on. So, and I also hope that the temporal dynamics, remember the slow frequency, and the topography, the spatial aspect, the three layer, are instrumental in understanding the sense of self on both psychological and psychiatric levels. So let me give you another example, consciousness. Another mystery of our times. There's a lot of discussion about consciousness, various theories of consciousness, which I summarized in the paper with Victor Lam in 2020. And the question, what is consciousness? And usually the approach by basically all theories, neuroscientific theories of consciousness, is that consciousness is special. So, and if consciousness is special, it requires a special neuronal mechanism in the brain. So that special neuronal mechanism, which is different from all other neuronal mechanisms, could be integrating information, integrated information theory, or global neuronal workspace theory, or predictive coding, or embodiment, or other specific neuronal mechanism. However, we assume the opposite. We assume that maybe consciousness does not require a special neuronal mechanism, rather the opposite. It requires the most basic neuronal mechanisms which are operating across consciousness and unconscious. Then it's just a matter of degree of that mechanism. And that, of course, we assume the brain's inner time and space to be key. So this is what we formulated in what we called temporal spatial theory of consciousness. Came out 2017. We have another update of that theory in a paper which is in revision in behavioral brain research. And the main idea here is that the temporal spatial theory of consciousness, the TTC, links spontaneous and task state activity. As you know, in the imaging community, in the fMRI community, there's sort of a joke. So when you submit an fMRI paper, you can get three kinds of reviews. So first, a reviewer say resting state is nonsense. Then you have another reviewer, tasks related activity is nonsense. And a third reviewer who says fMRI altogether is nonsense. So you see, we're really facing in current neuroscience a gap between spontaneous and stimulus related activity. We don't really know how they are related, and the assumption of the TTC is clear. Their relationship is key for consciousness. Second, as I said initially, we don't really know how neuronal and mental activity are connected. So specifically how neuronal activity is transformed into mental activity. So this is why we, so basically the TTC try to bridge these two gaps. Let me show you this slide, which is a complex slide. And, but I just want to highlight you. So the TTC assumes 4 temporal spatial mechanisms instead of just one like all other theories. And these 4 temporal spatial mechanisms are related to different dimensions of consciousness. So let me walk you through. So you have temporal spatial nestedness. I will explain later what it is. It's related to the level or state of consciousness. Then you have temporal spatial alignment, which is related to the form or the structure of consciousness. Then you have temporal spatial expansion, which is related to the phenomenal features of consciousness. And the last mechanism is temporal spatial globalization, where it spreads throughout the whole brain. It is related to the reporting or cognitive processing. So what I want to do now, and each of these mechanisms has its specific neuronal signs, feature as defined here, and they cross the boundaries between spontaneous, pre-stimulus, early stimulus, and late stimulus activity. And they can be tested. Each of these mechanisms can be probed and tested by different designs. So let me try to explain the first mechanism a little bit, so that you get a little bit more idea what I mean by that. So one key of our consciousness is that we have different time scales. So you have your consciousness over a very short time span, but you can link it also to longer time spans. Your self-consciousness, for instance, is over milliseconds, over minutes, and then also over hours, days, weeks, years, and decades, centuries not. Yeah. However, you see these are different time scales. And in consciousness, you do not distinguish between these different time scales. So how is that possible? How your brain, as I said, your brain integrates these different time scales for you. And that's what we call temporal spatial nestedness. Remember the nestedness from the Russian dolls. Different Russian dolls are integrated within each other, different sizes, same shape. And the same happens on the temporal side with different frequencies integrated with each other, meaning the faster frequencies are less powerful. They are embedded and nested within the next slower frequency, which is a little bit more powerful. And that one in turn is again nested within another yet slower frequency, which is even more powerful, and so forth. So you have, my beloved example of the Russian dolls or the Chinese crystal ball. And maybe if you have something similar, an example of nestedness in your part of the world, please let me know, because I'm really interested in that. So what do I mean by nestedness? So I already indicated the power law exponent. Remember the scale-free activity. You have the relationship here. Just indicate that here again. Here the frequency, here the power, more power in the slower frequencies than in the faster frequencies. And now the question is that related to consciousness? That's exactly what we probed in this study. This was done by a former doctoral student of mine, Jianfeng Zhang, who's now professor in Shenzhen in China. He did an fMRI study doing anesthesia. This was surgical anesthesia, important to consider. By the way, you can see that the sun is rising here in my office. That's why I blinded here. So what he did, so he did fMRI in the same subjects in the awake state and in the surgical anesthetic state. So, and he did a whole brain voxel for each voxel. He calculated the power law exponent. Remember, that was the relationship in the power between slow and fast frequencies. And no surprise, you can see a much higher power law exponent in the awake state. This is more red than in the anesthetic state. When you see the difference between the two states, you get this one. But this is not the interesting part. The interesting part comes now. So here you see the power spectrum. So this is frequency, this is power. This is 0.01 to 0.1. This is a typical frequency range of fMRI. Here you see the power. The red line is the curve for the awake state. No surprises here. You see strong power in the slow frequencies, less power in the faster frequencies. So this is a typical shape of the power spectrum. Slight variations between different subjects, but that's what you usually see. And the steepness of this curve This is what you calculate with the power law exponent. So now the same subjects in the anesthetic state. This is the blue curve. Look, the curve is completely flat. Yeah, there is no difference in the power anymore between these different frequencies, meaning all the frequencies are the same. Yeah, the temporal structure of the power spectrum is lost. So now go to the Mediterranean Sea, it's completely flat. Nothing changes. Yeah, it's always the same, monotony, complete flat, nothing happens. That's your power spectrum in the unconscious / non-conscious state of surgical anesthesia. Yeah. So, and here, of course, here on the lower right, you can see we calculated the PLE between anesthetic and awake state, of course, highly significant difference. So why is that important? So now you say, yes, Northoff, this is just neuronal. So meaning in your power spectrum, the temporal nestedness of the power relationship between slow and fast frequencies is lost. Curve is flat, it's no longer steep. There is no nestedness anymore. The faster frequencies are not nested within the slower frequencies in terms of their power anymore. The nestedness is lost. And this is very nicely illustrated by a schema which was done by another postdoctoral student of mine, Federico Ciglio, from Italy. You can see, so these are the time scales in the awake state. So you have milliseconds, seconds, hours, and so forth. And they correspond to these Russian dots, and you have a certain shape in your power law exponent in your power spectral density. However, now when you start the dating, the slower frequencies become relatively stronger and the faster frequencies become weaker. So meaning these time scales become abnormally strong relative to the faster ones. So your Russian dots, the curve becomes steeper. That's a typical, often observed slow frequency shift when you lose consciousness. However, when you completely lose consciousness, like in the surgical anesthesia, then your power spectrum is completely flat. Yeah. So meaning there's no difference anymore between different time scales. Remember my example of this Mediterranean Sea, it's completely flat. Nothing happens. There's no difference anymore. Meaning there's no waves. There's no slow and fast waves. There's no less and more powerful waves. Meaning temporally for these people, they don't perceive any temporal differences anymore. Everything is the same. It's just one homogeneous soup. That's the way I imagine the perception in these people. So imagine all Russian dots of equal size when you lose consciousness. Nothing happens anymore. So this is something which can be tested also on the perceptual level, and we're working on that. So now, how about spatial nestedness? Spatial nestedness means that a subset of regions is integrated and embedded / nested within a larger subset of other regions. So, and you can measure that. You can measure that, for instance, with the global signal in fMRI and the global signal topography. You can see that here. And here I show you a study which was published last year. Sean Tanabe and Zuri Wang, both former students of in my group, one from China, one from Canada, that even when you lose consciousness, your global brain activity decreases. And also the differences between the regions' activity also decreases. Meaning, in more professional terms, the global signal and the global signal topography decrease, and you no longer have any differentiation in your topography between the different regions. Meaning you don't have any topography anymore. Remember, everything becomes the same. And imagine if the size of all the Russian dots are the same, you don't have a nest in it anymore, and basically you don't have a Russian dot anymore, meaning you have no consciousness anymore. Yeah. So meaning the better your spatial differentiation between the different regions and the better your temporal differentiation between different time scales, the better for your consciousness. That's the main message. So it is not just about integration or global neuronal workspace, but it is really about the temporal and spatial differentiation of different scales. And that is described by the mechanism of temporal spatial nestedness in the temporal spatial theory of consciousness. Okay, let me go to the second mechanism, and that's indeed a key mechanism which I think really distinguishes our approach from others even more. So one key feature of consciousness is you experience yourself as part of a larger environment. Even when you look at me during this talk, you still experience yourself as part of your computer screen, and then that computer screen, you experience yourself as part of the context, let's say the table in which the computer screen is set, and the table again is set in a context, could be set, if it's nice and warm in Turkey, you might even sit somewhere outside on the terrace. In Canada, obviously, -5 degrees is not possible, so I have to sit inside. And that context is part of your experience. If you wouldn't have that differentiation between yourself and the context, you would not have consciousness. Early on, it has been conceptualized as figure background by the Gestalt psychologist. And what is important is really your environmental and bodily context in which you experience consciousness. So we call that temporal spatial alignment. Why? How is it possible that we experience ourselves as part of the wider environment? The only way for that to be possible is that your brain must somehow synchronize with your environment. Like when you dance to the rhythm of the music, you align, you synchronize with the music, and you experience yourself as part of the music. You feel the groove of the music. So you are aligned, synchronized with the music. Same with other things, with when you hear music, when you hear stories or read a book. Yeah, so this is what we call temporal spatial alignment as a key mechanism. So now the question, what are the mechanisms by means of which the brain synchronizes or aligns with this environment? One key component are the intrinsic neural timescales. What are intrinsic neural timescales? The brain has multiple temporal windows. So let's say you're sitting in a room with different window sizes. You see different things through the different window sizes. You see, for instance, the leaves of the tree of the branch in a very detailed view in a smaller window. But you do not see that as the leaves of a tree with a large trunk. You don't see that. For that, you need larger and other window sizes. If you have a very large vertical window size, you see the trunk, but you may no longer see the leaves as detailed. If you have an intermediate window size, you see the branches of the tree. You don't see the leaves nor the trunk. So what I want to say, you have different spatial windows, and the same applies to the temporal side. If you have longer windows and shorter windows, you perceive different things through these different windows. So, and your brain has exactly these kind of different temporal windows. You can measure them by the intrinsic neural timescales, for instance, the autocorrelation window. So what is the autocorrelation window? You correlate the time course of the signal with itself. You correlate time point, the activity at T0 with T1, T2, T3, and then T1 with T2, T3, T4, and so forth. So basically, you establish what is called an autocorrelation function. It's the degree of correlation. This is a time lax, and you see the longer the time lax, the lower the correlation of the signal with itself over time. So, and you can measure that, which for instance called the autocorrelation window. And interestingly, the autocorrelation window, other studies and our own studies clearly show that there's a hierarchy to them. So that the sensory regions have shorter windows. And that makes sense because they have to process this fast input. So you need shorter windows and they need to process it in a precise way. Whereas this default mode network or cortical midline regions, where remember the self, they have much longer timescales. So they have more longer timescales in their neuronal activity. So now the question is, how are these timescales related to perception? And let me show this here. So we had a paper last year, this year, where we showed that these time scales are abnormally long in the EEG when you lose consciousness. So you have only longer windows, but no longer the shorter windows. So everything in these longer windows is put together. You just see the trunk, but not the leaves. So, and this is based on real data on the autocorrelation function, as well as this is schematically depicted how they might perceive. So this is again by Federico Silio, and you see he has very nice figures. So because he does so nice figures, he has a reputation in my group of not being Federico Silio, but Federico da Vinci. So, so if you have shorter time scales and you have a variety of different time scales, you can really segment this scene like a police following a thief in its different time scales. So you have shorter time scales for each of these words or syllables. You have longer time scales for a whole word, and you have even longer time scales for the whole sentence. And visually, it's the same thing. So you can depict this action in time, so you can perceive him as separate, temporally distinguished, but you can also perceive that this one is related to this one because you have a longer time scale where it integrates these different stimuli. However, when you lose consciousness, like for instance in the early stages, like in N1 sleep, your autocorrelation window becomes slightly longer. So meaning you no longer have the shorter time scales to really segregate the different stimuli. What happens in your perception, it becomes a little bit more blurry, as you can see here. Now, if you even further prolong your time scales, meaning your autocorrelation window becomes even longer, like in N2 sleep or mild sedation, you perceive things even more blurry. Now, when you're in deep anesthesia, surgical anesthesia, or unresponsive wakefulness state or coma, you basically don't perceive anything anymore. It's just blank. Excuse me, let me just close the blind and I will come back in a second. So, too much sun here, and that's after all in Canada. So, so meaning it's completely blank. Yeah, you cannot segment the events in a temporal way anymore. Yeah, it's completely blank, and that's what you perceive. And this is indeed based on real data. So that really suggests the importance of the brain's time scales for consciousness. This is in the early stages of research, but we have more and more evidence that they are key. Now, how does this important? So the timescales are important for the stochastic matching between environmental and neural timescales. So if I'm lacking the timescales in my own brain for the fast rhythm of the music, like in tango, let's say, because I'm a German, I haven't grown up with tango, I may not be able to properly match and synchronize with the music of the tango. Yeah. If in contrast my timescales were tuned to that, I may be very much able to. And it is this matching which we assume to be key for consciousness. Why? Because in consciousness, you perceive and experience yourself as part of a larger, wider context. So, and we also finally, this is the last point on this one, that the temporal spatial mechanism can distinguish between different states of consciousness as indicated in this figure. For the sake of time, I don't want to go into detail. So let me skip this one and let me come right to the last example of psychiatric disorders. So here we raise the question, in depression, patients experience themselves as too slow relative to the environmental context. Nothing changes for depressed patients. Nothing. It's just everything is the same, no change. Yeah, and everything is too slow. Typical example, remember in China, a 16-year-old girl who was, let me tell you another example, which I recently encountered in Portugal, where I met a psychiatrist who was also a musician and a choir director. And he told me the example that very spontaneously one of the depressed patients came and asked him, could you make the YouTube music a little slower? It's too fast for me. And that's typical. If your inner time is too slow, your perceives the outer time as too fast. That's very typical. So this is why we conducted an investigation in the time speed of neuronal activity in bipolar people, bipolar patients with mania and depression. So main idea here, as I already said, you synchronize your inner time with the outer time. Yeah, and usually we are quite successful. You follow the time of the speed of my speech, and by that following, you are able to decipher the meaning and hopefully the main message of my talk. However, if your inner time is too slow, you will not be able to follow my speech because I'm simply too fast for you, and you will be stressed trying to follow me. You're desynchronized. And the opposite in mania. In mania, the inner time is too fast. That's what they subjectively experience, is high speed. And then, of course, the outer time is perceived as too slow. That is indicated here. If your inner time is too fast, you perceive the outer time as too slow. It makes sense because relative to the inner time, then the same objective outer time is too slow. And usually it's sort of a medium, both can relatively match with each other, whereas if it's too slow, you perceive the outer time as too fast. That's what happens in depression. That's why they're stressed and become frustrated, become sad, and then also withdraw. So now we said, how can we link that experience of speed to the neuronal speed of the brain? So first we said, okay, how can we measure neuronal speed? Speed is about change. How can we describe change in neuronal activity? By neuronal variability, change in the amplitude over time. That you can measure by standard deviation of the amplitude. Then how about the neurospatial basis? Inner time is known that your inner time speed is related to the somatomotor network. That has been shown in Parkinson's patients whose inner time is too slow. Whereas the outer time, we said, oh, maybe that's the first time when the external input is processed by the brain and its spontaneous activity, like in sensory cortex, like in visual network. So we took the somatomotor network neuronal variability as a proxy of inner time speed, and the visual network neuronal variability as a proxy of outer time speed. So, and what did we observe? So these on the right, this is a schema of the experience. On the right, these are real neuronal data. So we saw that the ratio between, and we calculated the ratio between inner and outer time speed / between somatomotor network and visual network. And you can see the red one is a mania. Here, the inner time speed is way much faster than the outer time speed. Yeah. Whereas in depression, the blue guy, you had the opposite. Outer time speed was much faster in the neuronal variability, higher neuronal variability in visual network than in somatomotor network. So that the inner time speed on the neuronal level was too slow, and the healthy subjects in between. So this amounts to different kinds of balances. So in the neuronal variability of somatomotor network, visual network, inner outer time speed on the neuronal level and on the perceptual level, they're relatively balanced in healthy, disbalanced in depression. The somatomotor network shows decreased neuronal variability, decreased inner time speed, whereas time speed neuronal variability was too high in visual network, upper right here. And in mania, you saw the opposite. Visual network neuronal variability is slow, and meaning they perceive the environment as too slow, whereas the inner time speed neuronal variability in somatomotor network was way too fast. So you have disbalances, and that's why we coined the paper too slow, too fast. I come to the end, last 3 slides. I hope I could show you that, albeit in the initial stages, that we try to look for temporal spatial features, topography and dynamic, as link between neuronal and mental features. You saw examples of topography in the self, the 3-layer hierarchy, and you saw changes in anxiety disorders. You saw different temporal and spatial mechanism at work in consciousness, temporal spatial nestedness, temporal spatial alignment, and you saw changes in the brains in a time too slow or too fast in bipolar, mania, and depression. So this is what leads us to say maybe we really need what we call spatial temporal neuroscience and dynamics of common currency. Here you see that we say topography is manifest in both neuronal and mental level. If your topography in the brain is abnormal, your perception and experience will also show an abnormal topographical / mental topography. Same on the side of the dynamic. If your brain is too slow, your sense of self and your sense of inner time will also be too slow. So this is what we speak of a common currency, which provide a linkage. So that's why on the basis of all these findings, I would like to, this is the second to last slide, I would like to make the plea that we really need a broader form of neuroscience, spatial temporal neuroscience. Currently what we are doing, we are looking at the brain and we're looking at brain function. Yeah, we look the neural correlates of different functions, affective, cognitive, social. However, we are missing mental features because it is clear that these mental features like self-consciousness, psychotic disorders cannot be traced to one particular function, but it's a constellation between these different functions. So that's why we say maybe we really need the spatial temporal approach. We call this spatial temporal neuroscience, which focuses on brain dynamics and brain topography, and that in turn we assume shapes your mental features, consciousness, self as in psychotic disorders, as well as subsequently your affective and cognitive function. So spatial temporal neuroscience is not in contradiction to cognitive neuroscience, but rather it's a broader, more encompassing framework. And my hope is that this spatial temporal neuroscience can develop not only on the systemic level, but ultimately also on the cellular level, because you can analyze your cellular data also in terms of time series with the same kind of measures, power law exponent, autocorrelation, I just demonstrated. And indeed, we have one study showing that. So this is sort of a more broader framework, spatial temporal neuroscience, within which then cognitive and affective neuroscience are just specific subsets. And with that, I would like to come to the end of my talk. Main message is clear: temporal dynamic, spatial topography connect brain and mind. And I hope you got some ideas and inspiration. And thank you very much for inviting and listening.
Well, thank you very much. It was really spectacular. I have learned lots of updated knowledge, and it was amazing. Thank you very much for this nice speech. And now talk is open for your contribution and question. Anyone like to ask question and contribute to subject? Yes, Gürkan.
Dr. Northoff, it was amazing. Thank you very much for this provocative presentation, and I mean, it's really moving. So a couple of questions I have. How do you position cerebellum in your interoceptive and exteroceptive and mental self processes? We know, I mean, in recent years, cerebellum has been implicated in such processes. So what do you think?
Yeah, I mean, a very good question. So I would definitely include the cerebellum in the whole thing because I'm a whole brain, holistic person. So this is clear. And I would say that each of these regions / like the cerebellum also, I know it's not a region, but contributes a certain spatial temporal feature to the overall temporal dynamic and spatial topography. And in the case of the cerebellum, particular temporal, I don't need to tell you that, it's very well known. It's for the precision of timing, it sends input to the basal ganglia. In schizophrenia, there's strong evidence that the cerebellum is also altered. So definitely, I consider the brain as a whole, and I would include in my spatial topographic and temporal dynamic view of the brain subcortical, all subcortical, cerebellum plus cortex. So it's not a purely corticocentric approach, though my examples are corticocentric, mainly because brain imaging, you know, it's difficult to get into the subcortical region. But so I consider rather the overall topographic structure to which the cerebellum contributes. And definitely in schizophrenia, it's also known to be altered. So no doubt, I would agree with that.
I think as the second question, do you see any correlation between the smaller time scale and intelligence?
Oh, that's a difficult one. So I would say it's tentative. I have no data on that, and I'm not aware that are data there on time scales and intelligence. You know, intelligence is a big field in the brain imaging.
Mm-hmm.
So intuitively, I would say is your number and repertoire of time scales is related to intelligence. So meaning if you have a larger span between slower and faster, a longer and shorter time scale, as well as a high number of differentiations in between, that should be related to intelligence. So unfortunately, I left that, I skipped that one slide I skipped. It's for, let me bring that back because it should be relatively fast. Here it is. So here we have, can you see this slide? So here, this is a schematic depiction where we say, okay, different species have different time scales. Yeah. And here, let's say the mouse, this is schematic, purely schematic, monkey, cat, human, they have different number of time scales, and obviously humans has more time scales than the other species, probably in part because the cortex is so vastly inflated. Yeah, because it gives you possibility of developing slower time scales because you have more spatial extension, which is usually associated with longer, slower time scales. And that, then if you have a higher number of higher number of time scales, which also more, so meaning larger frequency range, your bandwidth, literally, as well as a high number of different time scales within that repertoire, then you have a higher likelihood of having better stochastic matching with your environment. Yeah, better alignment. But that's a tentative hypothesis.
Great, thank you.
Well, may I ask one question, Georg? And I am wondering the really relationship between the spatiotemporal nestedness or neural time scales and the circadian rhythm. Is there any relationship?
Yeah, very good question. Of course, somebody who is in psychiatry and major depressive disorder and bipolar disorder, you have major circadian abnormalities. Yeah, you have the morning low and very typical. So absolutely, and you provide light therapy, you provide sleep deprivation. So no doubt. How that is related to the temporal spatial nestedness, in my case, it's hard to say because my frequency range is much faster than the 24 hours of the circadian rhythm. But intuitively and from a physicalistic perspective, I would say they nested within each other. How? I don't know. But it would be a key point for me to investigate because you have these longer temporal fluctuations in the mood of these patients. How that is related, I don't know. I ultimately would assume this 24 hours is part of your adaptation to the environment. Yeah.
Yeah, thank you. Bahar Güntekin likes to ask a question. Yes, your turn, Bahar.
Nice to listen to your talk, Professor Northoff. It's always a pleasure, face-to-face and also online. I would like to ask, you have already mentioned the evolution perspective. What about these dolls in evolution and maturation also? The number of dolls are decreasing or, with the low frequency and high frequency imbalance in the evolution and, with the maturation also with the child, are there less dolls or, the dolls are still the 7 dolls, but they're, their frequency is specific. It's something like.
I think you need a Russian to answer your question, but nevertheless, I will try. No, I think it's a good point. So I think that when you, as an infant, you have the propensity to develop a large biophysically constrained repertoire of time scales. Then which time scales will actually be really well developed and be fleshed out probably depends upon your environmental context. We all know this from musicians. You're exposed early on to music and so forth. And then probably certain time scales recede more into the background, are not as well developed, are not as abundant across different regions, whereas others are more prominent. And I think that's really strongly, that's where probably the environmental shaping sets in. And indeed, there is evidence, empirical side, and we published a paper on that last year, that traumatic life events strongly have an impact on your time perception and your time scales. Yeah. But that's
well, we have two more questions. Ahmed.
Hello. Dear Northoff, first of all, thank you really much for your great presentation. It was just a great pleasure for me. I have one question. What are the possible effects of meditation and music on sustaining this mental self-knowledge?
Yeah, you see me smiling. Yeah, exactly. So indeed, meditation is a very interesting case. So basically what I see phenomenologically in meditation, you indeed see a decrease in your mental self. You do not have no longer this self-referential cognition. Basically, you detach yourself from your own self. So this is often called in the meditation tradition, non-dual self-awareness. Yeah, so you still have a self, but it's no longer dual self-other distinction. And indeed, what you see, we just about to submit a paper on this, that you see a decrease in the default mode network, and you no longer see the opposition, the reciprocal or negative interaction between default mode network and central executive network. So meaning your topography really changes, particularly in proficient meditators. Yeah. Yeah. So it's really that sort of this three-layer topography is probably shifted from the mental layer towards the extra and interoceptive layer, particularly with the alignment to the environment, that you're more in synchrony with the environment, without, and that's very important, inducing anxiety in these people. Yeah. So that's phenomenologically interesting, but that can really be neuronally supported, that you have a shift from the regions, networks of the mental layer self to more the extroceptive, interoceptive self. I hope that addresses the question somewhat.
Yeah, a last question from Burak. Yes, Burak.
Hello. Did you do any studies with certain medications which would affect this nestedness?
Yeah, good question. Of course, as a psychiatrist, I have to consider that. So we did some studies early on with lorazepam, and indeed it changes some of these features. And indeed, your question is a good one. Does medication affect these layers of self or other therapeutic means? The problem with the drugs, they biochemically are extremely dirty with the antipsychotics and the antidepressant. They include all kinds of receptor systems. So you cannot really say it's just one specific serotonergic or adrenergic receptor system. However, what you can observe is that the subcortical, for instance, raffinucleus, modulates default mode network and non-default mode network in opposite ways. We had a meta-analysis and paper and data on this, I think last year or this year in molecular psychiatry. So indeed, you see certain changes in the topography. How those serotonergic induced or modulated changes in the cortical topography, how those serotonergic changes in the topography then affect the topography, the three-layer topography of the self, is indeed a very good question. The first step which probably would want to do in that, if somebody asked me to tackle that question, then I would probably see whether your biochemical fingerprints of, let's say, GABA, glutamate, serotonergic, dopamine are slightly different for the three layers of self. Yeah, so maybe that the GABA glutamate excitation inhibition balance is slightly different in the extroceptive layer than the extroceptive layer in the mental layer, which I would expect. That's the way, it's a very good idea, and it would be very interesting to pursue it and highly relevant, particularly for psychiatric disorders.
Thank you.
Well, thank you very much. Well, the other program is going to start very soon, and I am sure you have many questions, but promise we will invite you, Georg, to Turkey after the pandemic, and we will have chance to talk and to ask many, many questions. Once again, thank you very much for your nice and spectacular talk, and see you soon.
Yeah, thank you very much, and I appreciate and hope to see you soon in person. Yeah.
Thank you. Bye-bye.
Bye-bye.